This is a custom Raspberry Pi Pico dev board based on the RP2040 microcontroller. In this video, we will see what it takes to design an RP2040 based PCB project. This video is sponsored by JLCPCB, more on them later in the video. We will go through the hardware design, schematics, and prepare the output files needed for PCB fabrication and assembly. We will send the files to JLCPCB, get our board fabricated, and we will start writing some firmware test applications in C and in Arduino C++. Without further ado, let's get started with our project. Please note that this article and all of the articles we will reference today are linked down in the description if you wanted to check them out. First of all, we will start by having a look on the architecture of the RP2040 dual-core microcontroller. It's a dual-core ARM Cortex M0 Plus processor running at 133 MHz. It has a rich set of peripherals like an ADC, timers, PWMs, serial communication, etc. It has also a USB port. One interesting feature about this microcontroller that the internal ROM inside the microcontroller, the contents of this ROM flash memory inside the microcontroller itself is hard-coded while fabricating the silicon chip itself. And here is how it works. First of all, you need to connect an external quad SPI flash external to the microcontroller, and you need to connect the USB to a USB port in your PC. This is a USB, and this is the quad SPI flash. If you hold the boot pin of this microcontroller while connecting your USB to the PC, it will get detected as a USB mass storage device. Then you can drag and drop your firmware UF2 file, and your code will be flashed by the processor into the quad SPI flash memory, and this is the job of the firmware in the ROM memory. Then after booting up, the processor will be executing the code that you have flashed to the memory through the XIB or the execute in place interface. And this is what may be different in this microcontroller and the others in the market. This is the datasheet and the reference manual documents that we will need while designing the hardware board. This is the microcontroller's datasheet. 640 pages. It has everything that you may need to know about the microcontroller, especially the pinout and the functions of each pin. And this is the datasheet of the official Raspberry Pi Pico dev board. You will also find the schematics of this board at the end of the document, right here. And the final document is the hardware design guidelines for the RP2040 microcontrollers. And this is what we are going to use today. We will build a minimal design system around the RP2040 microcontroller. This is the quad SPI flash. This is an LDO oscillator and the USB connector. This is pretty much everything that we need. You will find a lot of information in this document. The power supply section, the decoupling capacitors, how to place the decoupling capacitors, the flash memory, etc. You will also find more information about things like VGA, SD card, and audio. There is a lot of information in this document. I think you need to check it out as well. Let's get back to the schematic of the minimal system. Here it is. This is what I referenced while making my dev board. And let's get back to our project and see what I have came up with. Here is the schematic. First of all, we have our USB-C port. It can be a micro USB, whatever, but we need to have a USB port because this is the way to flash this microcontroller, and we can also use it as a USB CDC class and send some serial print messages from the microcontroller to the PC. The CC1 and CC2 resistors for power negotiation for the USB-C, and this is an LDO to regulate the USB voltage from 5 volts down to 3.3, which we will use it to power up our microcontroller. This is the quad SPI section. The chip select pin of the quad SPI flash can be pulled down to ground using this push button to start flashing a new firmware. Here are some indicator LEDs, and let's check the microcontroller circuitry. Those pins are connected to the quad SPI flash, and those are the USB data lines. As you can see, we need to have a 27 ohm resistor, and this information is also found in the hardware design reference guide. As you can see here in the USB section, that you need to have 27 ohm termination resistors for the USB in order to meet the USB specifications. And this is our 12 megahertz oscillator that goes to those pins. There is a serial wire debug port that consists of those two pins. I will connect them to this I/O port, and I am using some of the I/O pins, not of all of them. However, in your case, you may need to expose all of these I/O pins. If this is what you need in your application, then you need to use a larger I/O port header. But for my test application, I'm using the EDC pins to build a capacitive touch application, as we will see while testing this board. But you can use the I/O pins however you wish. Here is the reset button. The run pin is connected to this reset push button, and it's internally pulled up, so there is no need to externally pull up this pin, but it's recommended to have this capacitor in this place to prevent any unintended reset condition in your system. Last but not least, the power section of the microcontroller. This is the 3.3 input pins. As you can see, those 4 pins need to be connected to the 3.3 line, and those are the decoupling capacitors that are recommended in the hardware design document. One interesting thing here is that we have a 1.1 volt line from this microcontroller, and here is how it works. The RP2040 core needs a 1.1 volts, so there is an internal LDO voltage regulator and here is the input pin for the LDO, and the 3.3 goes into this pin, the VREG in, which connects to the internal LDO. The internal LDO gives out a 1.1 voltage, which is the VREG out pin. Here is the 1.1 voltage, and we will connect it back or feed it back into this DVDD pin, which needs the 1.1 voltage. And these capacitors are the decoupling for the core voltage supply. And this is everything about the schematic. Let's jump to KiCAD, and this is our board. Let's get to the 3D view. Regarding the components layout, it's very simple actually. You need just to have the QSPI flash as close as possible to the microcontroller itself. You also need to have those USB termination resistors as close as possible to the chip. You need to have the decoupling capacitors as close as possible to the chip as well. I believe everything else is pretty much point-to-point connections. And in my case, the capacitive touch sensors need to have no ground around them. So there is a keep out area around the CapTouch sensors to reduce any parasitic capacitance that may decrease the sensor's sensitivity. And that's all. Let's get back to the PCB view. This is the plugin that I use for generating the PCB fabrication files for JLCPCB. With one click on this button, you will have all the fabrication files needed by JLCPCB, and we can head over to JLCPCB website to place our PCB order. A huge thanks to JLCPCB for sponsoring this project video. They offer high quality PCBs for affordable prices, up to 4 layers, just $2. There is also a huge discount on 6-layer boards at just $35, and this option has free VIA and pad. They also offer flex PCBs, PCB assembly service, multicolor PCB. They offer 3D printing, CNC machining, and a library of mechanical parts if you need to. And they have now collaborated with Raspberry Pi, so the new Raspberry Pi Pico RP2040 microcontroller is now in the SMT library from JLCPCB. There is the A version and the B version, and there is an upcoming project based on this microcontroller, so stay tuned for this. Unfortunately, the 4 version of this microcontroller is not in stock yet. The nice feature of this specific variant is that it has an internal flash memory, so we don't need to have an external QSPI memory and extra components in the BOM. So it may be better to use actually. However, the RP2040 is also an upgrade, even if it needs an extra QSPI external flash memory. It has 8 PIO state machines, which is more than what we have in the RP2040. And the B variant has 80 pins, which is more than what we have here. So it's an upgrade overall. Anyway, let's add our Gerber file. Here is my Gerber file, and as you can see, it has picked up my design. The board is 4-layer board. Enable the assembly and select quantity of 2, assembly on top side only, economic assembly. If you have clicked here black, this will go to standard assembly and it's not economic anymore, and this option will cost you even more. So I will click here. Let's have another check. Those options will be the same, so I will click next. Then we will click next again. Here we will upload the BOM file and the component positions file. Here is my BOM file, here is the positions file, and process. As you can see, it has picked up all the parts in my design file. And here is your last chance to optimize the cost of your board if you can, by checking the basic and extended components. For each extended component, you are going to pay 1.5 USD. So if you can replace any extended part with a basic part, I believe you should do so, as long as it has the same footprint and it will not ruin your overall design. But in my case, I have done this already before reaching here, so I will proceed. Now this is the component positions or the placement that the system has picked up. This might be wrong sometimes, so we will right click and drag it in the middle, zoom a little bit. First of all, you need to adjust this. I believe this is not mandatory, they fix it on their own, but if you can do something like this, I believe you should. Let's move to the 3D view, check it from the down. This is now much better. For this reason, you may have to include some silk screen indicators to help you judge the component placements. Like this LED, for example, I know that this is connected to the ground, so this is the negative side. Or you can also check the KiCAD file and make sure that it's placed correctly. However, if you have a minus or plus indicator to decide which side is the anode or the cathode, it will be much better. The same goes for the ICs as well. The last step to place our order, we save it to our cart and pay for the order and wait for the PCBs to arrive. Here are my boards after receiving from JLCPCB, and now it's time for testing. First of all, the Raspberry Pi Pico or the RP2040 microcontrollers can be programmed using C, C++, Arduino C++, MicroPython, CircuitPython, Rust, and many other options. In this video, for the sake of simplicity, we will use C, and we will also use Arduino C++. However, you can check my website for other guides. This is the first guide, which is getting started with the Raspberry Pi Pico using C++ SDK. And this is the getting started tutorial using C++. You can also use Arduino, MicroPython, CircuitPython. This guide will show you everything that you need to know about the C++ SDK from Raspberry Pi, the software stack of this SDK, how it's built, what is the CMake file, everything that you need to install, the whole tool chain and how to install it step by step. At the end of this tool chain installation process, you will have the Pico Visual Studio Code executable file shortcut on your desktop. And this is what we will use for developing C applications for the RP2040. And the first firmware example is to blink both LEDs on our board. And I'm speaking about those LEDs, LED 1 and 2. We will blink both LEDs by creating a new project. In order to create a new project using C++ SDK, we will get back to the guide for the C++ SDK. Step 1, create a project folder, empty directory, name it however you want, but this is the name of our project, and create a main.c source file and keep it empty. Then create an empty text file, name it cmakelists.txt, and this is the code that you need to include in your cmakelists file. And this is the name of the project directory or the folder that we have created first, and save this text file. Last step is to copy the Pico SDK import.cmake, the source cmake file from the SDK folder. And this is where you will find this Pico SDK import cmake source file. After copying this file to your project directory, you will have the main.c file cmixlists.txt file and the Pico SDK import.cmake file. Those are the 3 files in your directory right now. Then you need to open up the Pico Visual Studio Code executable file, which is the shortcut that I have shown you on the desktop, and now navigate to the folder which we have created for our project. Then after opening up the project, you can click on the build button to build the project and take the outputs and flash it to the microcontroller. This is the guide for the C++ getting started. We will get back to our custom PCB project and we will implement the same steps to test the LEDs on our board. Here is the folder that contains the 3 files needed, the CMake lists. The name of this project is GPIO demo, which is the name of the folder that I have created. Now I have opened the Pico Visual Studio Code. I will click on File, Open Folder, and navigate to the directory of my project. Now I have selected my folder, the GPIO demo. The build system has detected everything, as you can see here, and it has created this build file. The C code in this project defines 2 GPIO pins for the LED number 1 and number 2, which are those pins. If we get back to the schematics, LED 1 and LED 2 are connected to the GPIO number 22 and 23. Let's get back to our code, and these are the IO pins used. I will init the pins, set the direction to be a GPIO output, then we will set the states to 0, 1, a bit of delay, and 1, 0, and a little bit of delay. So our 2 LEDs should be toggling alternatively. Now let's build our project using this build button. As you can see, it has completed successfully, and if we navigate to the project directory, now we have this new folder for the build outputs, and this is the UF2 file or the USB flash format file that we need to flash to our microcontroller. So here is what I'm going to do. Let's open this up. I will connect the USB to my PC. Now it has been connected and the power LED is showing up. Here is what I'm going to do. I will hold the boot button and keep holding it. Then I will click on the reset button once and release it while holding the boot button. And voila. And this is our Raspberry Pi Pico device. We will get back to the build outputs. We will open the Pi Pico storage and drag the main.uf2 file into the memory, and it will get connected, and now our board is blinking. And this is how easy it is to flash firmware using the UF2 format. After passing our first test, we will also test the serial printing using the USB. As I have illustrated earlier, that the USB port that we have on the Raspberry Pi Pico is used for the flashing of the firmware, and it's also used as a USB. We will use the USB CDC class to send some serial messages from the microcontroller to the PC. This is our next test project, and this is the tutorial guide for the USB serial printing using C++ SDK. Here is the tutorial using serial over USB. There is a bit of information here before starting the actual project if you want to check it out. Step number 1 is to create a folder for the project. Create a main.c file, copy the application file in the main.c file, make the cmake list.txt file, which is different from the Raspberry Pi Pico and Pico W, whichever you have, but in my case I will use the Pi Pico version. And the last file is the cmake source file. We will copy it into our project directory, and this is what we will do in this USB serial print test example. We will print the message hello world with a delay, and we will keep printing this message. Let's get to the actual project. Here in the cmake lists, there is a bit of difference from the last project. Those 2 lines of code will do the following. The stdio function calls that we are doing here in our project, this printf function, is now enabled over the USB, and we have disabled it for the UART. So the serial print will be routed to the USB port instead of the UART. This is what it does. Then let's open this project directory from the Pico Visual Studio Code, File, Open Folder, and navigate to the Hello World application. And it has automatically detected and picked up everything in our project. We will click on the Build button. It will start building the project, and it has built successfully. We will get back to our Hello World application. Now we will find this build output file, and here is our main.uf2. Again, my board is connected over a USB to my PC. I will hold the boot button and hit the reset button once. And here we are. Let's open the build output, and here is the Pi Pico device. We will drag the UF2 file. It will flash, and now we can open like Arduino terminal. Choose the port, serial, and here is our message. Now we have successfully completed our second test. For more information about the USB serial print using C++, you can check this tutorial, which we have seen here. And now let's move to the Arduino C++ programming for our custom PCB. There is a guide for the Arduino, as I have told you earlier. This is the Arduino Getting Started guide with Raspberry Pi Pico. There is also a MicroPython, CircuitPython tutorial if you want to check them out as well. To set up your Arduino IDE with Raspberry Pi Pico, for sure you have to have a version of Arduino IDE installed on your system. Then you will head over to the Arduino IDE, Preferences, Additional Board Manager, and add this URL. The URL is here. You will copy this into your Preferences window. Then in your IDE, go to Tools, Boards, and select the Board Manager and search for the Pico. You will find it here and click Install. And now you have installed the Arduino core for the Raspberry Pi Pico and the board definitions for all of these boards. And now let's program our board using Arduino C++. Again, we will do the same test. We will blink those two LEDs alternatively, but using Arduino C++ instead of the C SDK. Here is the test application. It's pretty much the same thing. I am defining the two GPIO pins for the LEDs, writing high, low, delay, low, high, delay, and it will be repeated. The board is connected to my PC. I will go to Tools. Here from the Board Manager, I will select the Raspberry Pi RP2040, and here are the Raspberry Pi Pico boards. I will select the generic board because I have a custom designed PCB around the RP2040, so I will use the generic option. And now we will open the same menu again, and we will have all of these options for building and flashing code for the RP2040. Flash size is 16 mega, no file system. I will check this option, and I will keep everything as it is. In order to flash this code, I will do the same steps. I will hold the boot button, and I will hit the reset button once. And now we don't need this menu. We will click here in the tools, check the port, and select the UF2 board. This is the option, and we will click on the upload button. It will compile and flash our code. It's taking a bit of time, and it has completed successfully, and the board is flashing the LEDs as you can see now. Let's get back to our project. I forgot to mention the QSPI flash memory in our design. For this board, I have used this specific QSPI flash memory, which is 16 megabyte memory. You can also use 8 mega, 4 mega, whatever you want. But I believe the 16 mega is the maximum limit for the flash memory in order to be addressable by the execute in place interface. The XIP interface inside the RP2040 microcontroller will address up to 16 megabyte of addresses for the flash memory. You can, I believe you can use a larger flash memory for firmware and storage at the same time, but I didn't check this feature in detail, and that's all about it. One last application to check out is the reason behind designing this board actually, which is evaluating the possibility of using this microcontroller in capacitive touch sensing applications, and those are the two touch buttons. And here is a demo for the capacitive touch sensing application, which is actually working. However, it didn't meet my expectations in this kind of application, at least compared to the WCH RISC-V microcontroller that we have seen in a previous project. Anyway, I hope you have found this helpful to build your own custom PCB around the RP2040 microcontroller. If you do, you can consider subscribing to this channel in order to get notifications for the upcoming videos like this RP2350 PCB project that I will publish in the near future. I'm signing out, and I will catch you in the next one.